Good evening. Yes, I have started recording. So, good evening, everyone. Welcome to the 11th session of Aspen Plus Simulation Software, a basic course for beginners. So, most of you requested that assignment 8 LHHW Kinetics problem was issue for everyone, I guess. Most of you are facing issues like how to add those coefficients. Am I right? Or any one of you solved it correctly? Hello?
Yeah, not sold.
Okay. Dhruv, for you. Okay, so let's take that problem today and let's learn how to add those coefficients for adsorption terms. So, sorry. Okay, we'll start our session with this LHHW kinetics problem of assignment 8. So, for that, we have a reaction, this generalized theory, so that they have considered the reaction as W plus X gives Y plus Z. So rate expression will be K into exponent of minus E by RT, right? Now KF says the meaning of KF is forward reaction and KB is backward reaction. So if the reaction is forward, we need to add, I'm sorry, why I don't know why is that happening. So the if forward reaction is there, so it should be KW. It should be KF into concentration of W into concentration of X, assuming that reaction is first order with respect to both W and X, and minus KB for backward reaction with Y and Z, assuming it is first order with respect to Y and Z, divided by adsorption expression. So for this case, we are assuming, I'm sorry, for this case, we are assuming that the reaction is irreversible reaction. So our rate expression will be like this because there is no backward reaction, so we don't need this term. So it is just multiplied by 0. It stands. That means that this part is not available. So we have just this part divided by adsorption term. And I guess this was similar. This is similar to your problem statement. We will see that problem statement. So for this kind of reaction, here Kf is equal to 1 and Kb is equal to 0. That means there is no backward reaction. There is only forward reaction. So this is irreversible reaction. So for that, we need to choose LHHW type from the drop down list. We need to define our reaction. We will do that. We need to add the values of K and E. This is the value of K and E we need to add first. And then under driving force option for term 1, we need to add all coefficients A, B, C, D 0. And for term 2, we need to add very large negative value for coefficient of A. And other than those values are 0. So this actually we discussed about for PFR, this numerator term, but we never discussed this adsorption term, that is denominator term. So for that adsorption expression is given by 1 plus Kw into W plus Kx into X plus Ky into Y plus Kz into Z raised to N. Don't worry about this. We will see. We will implement how to do it. This N we need to take care, and this Kw values we need to take care. So this K, whether it is Kw, whether it is for any of the component Kw, Kx, Ky, Kz, this K is in this term ln in Aspen. This K is in this term ln K is equal to AI plus Bi by T plus Ci ln T plus dit. So what we need to do, we need to convert this Kw term into this ln K is equal to this term, and we need to find A, B, C, D values. So let's do that with this same assignment 8 problem. So I have just copied from there and pasted here. So let's read out the problem first and then we will try to solve it. A gas phase oxidation of chloroform is taking place inside multi-tube plug flow reactor, and the reaction is given like this: 2CHCl3 plus 2 water plus oxygen O2 gives 2 CO2 plus 6 HCl. And for that rate is given as this here you can see that 1 into C concentration of CHCl3 minus 0. So this means that our reaction is irreversible reaction. So here we can see that if we compare both things, it's similar to this K into, if we compare this and this, so it is K into exponent of minus E by RT into 1 into this W into X. So here rate is dependent on CHCl3 only. So it is just CHCl3 concentration of CHCl3 divided by this adsorption term. So adsorption term should be like this, but we have like this K into some, if we consider this whole part as K, so K into concentration plus K, this whole term as K into some concentration. So here it's like that 1 plus K into concentration plus K into some concentration to the power whole to the power n. So here whole to the power n is 1 because there is no term. So this is power 1. So n is 1 here. So here rate constant is in second inverse. This means the reaction is first order, and we can see this from here that rate is dependent on concentration of CaCl3. And the concentrations are in kilomole per kg. R is 8.314. Choose the chemicals with metric units template and set the property method to UNIFAC. Okay, so this is the problem statement. The feed stream is flowing at a rate of 150 kilomoles per hour, where all the components are in their stoichiometric ratios. So no flow rate is given, but we need to assume that those are in their stoichiometric ratios. With inlet temperature and pressure as 100 degrees Celsius and 1 atmospheric pressure respectively. Temperature, pressure, and flow rates are given. The PFR is operating at 100 degrees Celsius and has 10 tubes. The PFR has a length and diameter of 1.2 meter and 0.6 inches respectively. Here you need to be careful. One unit is in meter and one unit is in inches. The pressure at the reactor inlet is 1 bar for the process stream with 0.2 bar pressure drop. Catalyst to it is given as 2000 kg per meter cube. The bed voidage is 0.5. Run the simulation and answer the following questions. Okay, so we are supposed to answer some of the questions. So before that, we will try to simulate this problem. Okay. I assume that all of you are having the problem statement, so there is no need to take screenshot of the problem statement, right?
Yes,
Okay,
sir.
those
Already have the problem statement.
okay, those who joined late, just want to share, we are solving assignment 8 part B problem. So okay. So first let's add the components. So we have CHCl3, water, O2, CO2, and HCl. So we need to add CHCl3.
Just a second. I would.
Yes.
So, am I the only one who is not able to load the Aspen currently? I'm trying to load the Aspen since last 10 minutes, but I'm not able to connect.
Okay, anyone using IIT Guwahati license, please respond. Okay, Sudhanshu has raised his hand. Are you using IIT Guwahati's license, Harshil? I guess so.
Yes, yes.
Yes, anyone, Dhruv, which license you are using?
Sir, it is loading for me currently. No, it is showing a licensing error, sir. License checkout failed.
Okay, so I guess it is some issue with your IIT Guwahati license. I don't know how to help. Maybe it's some issue from their side, not from you. Manish, are you able to?
Yes, I am able to use,
Oh, he is
but
able to
I have
use.
not used from 2 3 days. I have not used.
Okay. Harshil, is this latest or you told it was last week? It was for you last week also.
No, it's version 12 only, not 14.
Okay, okay.
I'm using 14 version 14 V14.
Okay, can you check, please, if it's possible for you?
Yes, sir, it is not working currently.
Yours is version 12 or 14? True.
Sir, mine is version 14.
Oh, 14 is also not working. Okay, I'm not using, I'm using IT Bombay's license. I suggest you to I suggest to those who are facing this is to write down one email to professor. Maybe he will solve that. Okay, so let's solve this problem. So we have so I just want to know who are solving right now with me. No one.
I intended to solve but couldn't.
Yeah, okay. Okay. So let's just see. We are I'm sorry. Where were we? Yeah, here. We are adding CHCl3, water. Water will be, I guess, from here only. Water. Sorry, it's here. O2, CO2, and HCl. O2, oxygen, CO2, carbon dioxide, and HCl, hydrogen fluoride. So we have added all these components. I just want to know if someone is solving right now or not. Okay, I guess no one is solving. So okay, we have added all 5 components of our interest. Now we'll press next. Okay, so which property method we are supposed to use? We are supposed to use unifact model. So here in problem statement, it is written property method to unifact. So we will add unifact from here. Unifact. Okay. So required inputs, required properties input complete. So now we can go to simulation scene. Okay. So what is told to us? We are supposed to use a plug flow reactor. So let's first go to the reactor and add a R plug model. So we added R plug model. We will be adding one feed stream. One feed stream and one reactant stream and one product stream. Okay, I'm just doing this. I'm in blocks. Okay, so here I will be writing reactant. I don't know if okay, yeah, we can write reactant and product. Okay, and this is R plug, PFR, plug flow reactant. Okay. So now we will add our reactant conditions. Reactant conditions. What is told to us? I'm sorry, it's here. Yes. Um, the feed stream is flowing at a rate of 150 kilomoles per hour with inlet temperature 100 degrees Celsius and 1 atmospheric pressure. So here temperature is 100 degrees Celsius and pressure is 1 atmospheric pressure with 150 kilomoles per hour. Okay, now here we need to add some conditions like it is told that all the components are in their stoichiometric ratios. So what should we take? Can anyone tell me?
Psychrometric ratio 2 to 1.
Yes, 2 to 1 is given. So how should we take the input here?
It should be in mole fraction.
We can take any value. Let's say uh, let's say mole flow rate is in stoichiometric ratio, right? So I'm sorry, where? Yeah, here. Total flow rate is given as 150. And let's say that mole flow rate of oxygen O2 is X, right? So 2x plus 2x plus X is equal to 150. Correct. Correct. Okay. Here it is written in where did it go? In their stoichiometric ratios, right? So let's say that it is in X, molar flow rate of O2 is X, then H2O will be, this term will be 2X and this term will be 2X. So 5X is equal to 150, so X will be 30, right? So molar flow rate of water will be 30 and these two terms will be 60 and molar flow rate of O2 will be 30 So rest two terms will be 60. Am I right? We don't need to mention. Okay. Am I right? Please respond. Any one of you. Is this clear? How did
Yes,
I
right,
take?
sir. Yeah.
Okay. So we added molar flow rates. Just we need to take care that we have to take molar values, right? Okay. So let's go ahead. We'll press next. Okay. So what is the reactor type here? What should we add? Let's go to problem statement once again. So what should be the reactor type? The reactor inlet temperature and pressure are 100 degrees Celsius and 1 atmospheric pressure, and PFR is operating at 100 degrees Celsius. So which option best suits from here? Anyone?
Reactor with a specified temperature.
Yes, because temperature 100 degrees Celsius is given.
Yes.
So I am choosing reactor with specified temperature. And what is the temperature? That is same as feed condition, right? 100 degrees Celsius, and PFR is also at 100 degrees Celsius. So we'll choose here constant at inlet temperature. Correct? Okay. So there is no input left for this part. So we'll press next. So it will go to configuration. Okay. So what type of reactor it is? It is multi-tube plug flow reactor, right? So we need to choose here multi-tube reactor. And what is the number of tube? That is, there are 10 tubes available. So I will choose 10. Okay, diameter varies along the length of the reactor. No, those kind of information is not given. Okay, so let's go ahead. The PFR has a length and diameter of 1.2 meter and 0.6 inches. So 1.2 meter length and diameter is 0.6 inches, right? Okay. Should I change here process stream vapor only to something else? Should I change here from process stream in vapor only to something else? Anyone? Please respond. Okay, let's
Liquid.
read. Sorry. Hello.
Gas phase after process.
Okay,
It's
yes.
vapor
So
only
okay, so let's
because it
keep
is a
it like
gas
this
phase reactor.
only. Yes. So let's keep it like this. We need to add reactions. Let's come to reaction part later. Let's complete another inputs. Okay. So here, the pressure of the reactor inlet is 1 bar for process stream with 0.2 bar pressure drop. So here, process stream is at 1 bar with pressure drop of 0.2 bar. Is this clear? 1 bar for process stream with 0.2 bar. So here we have added 4 process stream. Okay, so hold up. I don't think we have anything. Catalyst. Okay, so we are given some details for catalyst. The catalyst of density 2000 kg per meter cube is used, and the the bed voidage is 0.5. So let's add this. So catalyst is present or not? Yes, catalyst is present in the reactor. So we need to give some value. So we are having two options, catalyst loading and bed voidage. We know the value of bed voidage, that is 0.5. So we'll add 0.5. Okay, the other input is we know the catalyst density. So here we will choose particle density. The value is 2000 kg per cubic meter. So we'll choose 2000. Uh, okay, let's change first unit kg per cubic meter and 2000. Okay, so we have added this. Okay, so I assume we have added all these inputs, right? So now we are left with reaction part. So we'll go to reaction. Okay, so first we need to define a reaction. So from here, I will go to reaction. I will choose new. Okay, the here, what kind of reaction we are supposed to take? This is LHHW. From this term, you should understand that this is LHHW kind of model. So we will choose LHHW and we'll press OK. So now we need to define our reaction. So what is the reaction? Reaction is CHCl3 water O2 CO2 HCl. Let's first add component CHCl3 water O2 CO2 and HCl. And what is the stoichiometric coefficient? Can anyone tell me? I guess it is 2 minus 2. I'm sorry.
2 and 1.
2 1. Then for CO2
Sir, 2 CO2. So 2,
and
6.
HCl 6
6.
HCl. Okay. So we have
I have a
defined
doubt.
our yes.
So I saw one of the tutorials by sir.
Yes.
I guess it was in week 11 or 12. So it is also regarding the LHHW. So while
Okay.
selecting the reaction, he said that first you should select this general type. If you just
Sorry,
go
sorry,
to
sorry. You should
your,
select.
the reaction type is general. If you just could go to your Aspen screen,
Yeah, there is
Actually,
one option
Prasan
of
sir,
general. Yes.
and then from the
actually,
selection of general, then you should select LHHW. So is this the same way, or is there any difference between these two methods?
No, I don't know. I have not done anything like. Is this in lecture 11 or 12?
so in last lecture,
Yes.
Saha sir has told the same, which her Manish is saying all right, right?
Yes. So I guess it's lecture. Let me just check.
32. It is lecture
In that
32. Today
particular
only
lecture,
I.
Saha sir said first choose the general type. After that, you have to select as like the LHHW.
Right.
Okay, so do you want to do like that? I don't have any issue.
No,
It,
you
it
don't
should
have,
be
but
the same.
there is
Should be
I
the same.
at
confusion.
least
Just
so for okay, let me say I am directly choosing this LHHW and my answers are matching with those assignment answers. I
okay.
am
Okay, okay,
directly
okay,
choosing LHHW. If you want, we can
okay.
try with general then LHH. I don't know. Sorry, what was the lecture number? Can you guys tell me? I will check. 32 or
Is it 32 isobutene production plant? I think.
okay, it's in week 11, right? Or 12.
In 11. Please
Okay.
confirm.
In 11.
Okay, it's 32. Okay, I will check it. I'll check that. But for these, at least I have directly solved for LHHW and my answers are matching.
Okay. Okay. No issue.
So, okay, we have defined our reaction that is 2CHCl3 plus 2 water plus O2 gives 2CO2 plus 6HCl, right? Okay, so now we need to define kinetics. We'll go to kinetic. Okay, so here we need to change one thing, reacting phase is right. And what should be the rate basis here? It should be volume or catalyst.
Catalyst base.
Why catalyst?
Actually, catalyst density mentioned here
Okay,
in
so
the
we need
question.
to consider catalyst, right? Okay, so I will choose
In
catalyst. Wait.
problem also.
Yes.
Yeah, so in problem, if we look at the units, it is per kg, so that tells us that we have to choose catalyst basis.
Yes, this kilomoles per kg. Concentrations are in kilomole per kg. This thing, this term, right?
No, no, he's asking about the catalyst unit.
That is in kg per cubic meter.
That
Here,
density.
density is in kg per cubic meter. I'm sorry, I didn't follow. What are you trying to ask or say? Ashutosh? Okay. Okay, so now we will be adding. Okay, so main game is here. So let's first compare this with here. So it is k into exponent minus e by rt. W, we have this term, right? This term in numerator k e raised to minus e by rt 1 into w into x. So we will compare that with our question. So we have Just a minute. Okay, we forgot to do one thing. We need to choose what was the template. It was metric units. Okay, I guess we need to change it to metric units because this K, I guess K value will be according to that units. Okay, so here K will be what will be the value of K if we compare it with our that theory part. If we compare it with this thing K e raised to minus e by RT 1 into Wx. So that is our numerator. So what should be the value of K? K should be 3.72 into 10 raised to 5, correct?
Sir.
And
Yes, sir.
acquisition energy should be
21,700.
21700. But what should be the unit of activation energy?
Sir, this kilojoule per kilomole.
Why kilojoule per kilomole?
Sir, because it is consistent with the units of R that is
R.
there.
Correct. So R is in kilojoule per kilomole Kelvin. Temperature is in Kelvin. So E should be in kilojoule per kilomole uh, to make it unitless. Okay, so let's add value of K as 3.72 into 10 raised to 5. So 3.72 E plus 5. So that is value of K and activation energy is 21700 kilojoule per kilomole. 210 kilojoule per kilomole. Okay. Now we'll go to driving force option. Okay, so we need to add concentration exponent for term 1. So what should be the concentration exponent for CHCl3 from this reaction? It should be 1, right? It should be 1, right? Please respond. You can see that this is K into e raised to minus e by RT, and this forward reaction, that is term 1, is 1 into concentration of CHCl3. So that is dependent only on concentration of CHCl3. So here it will be only 1 for this term. Is this clear or not? First tell
Yes,
that to
sir.
me. Okay, that is clear. Now we need to add coefficients A, B, C, and D. So here the coefficient is 1 for CHCl3. If we compare it with this thing, so that is nothing but basically some Kf is equal to 1. So if Kf is equal to 1, what should we add here at A, B, C, D term? Here it is already written that all should be 0. But why all should
Yes,
be
sir.
0? Why all terms should be 0?
Because it is a single phase reaction.
No, nothing to do with single phase. See, your value of K is given as 1. So if you add K is equal to 1 here, you will be getting values of A, B, C, D, right? So ln
ln1
K
is 0, 0.
is equal to ln1 is equal to 0. So that means temperature can't be 0,
ln,
right? So all your A, B, C,
yes.
D terms are 0. So we need to
ln,
add value of A, B. Okay, it automatically takes 0. Is this clear? Is this clear?
Yes, sir.
Okay. So we have added CHCl3 1 and all the other terms as 0. Now we need to add for backward part, term 2. So there is no backward reaction, right? So all this term won't be there. Now, what should be the value of ABCD? What should be the value of ABCD? If we compare with here, so 0 into Y into Z. So ln0, what is the value of ln0? ln0 is minus infinity. So only A can be very minus infinity means very large negative value, right? So we'll add for A, these terms can't be minus infinity, right? B by T, C ln T dt. So we will just add for A as very large negative value as it is ln0 is minus infinity and other terms B, C, D as 0. So let's add some minus very large negative value. So minus 1 E 9. Okay, so these are very large negative value. Large negative value means the number is large with negative sign. So I will just please. Okay, so we have added this driving force term. Okay, is this clear to everyone? This first term, numerator term, we have completed.
Can you please just summarize?
Okay, so our numerator term was k into e raised to minus e by rt, 1 into w into x minus 0 into y into z. So first we added k and value of E for the reaction. If we compare this expression and this expression, we have value of k as 3.72 into 10 to 5 and E as 21700. Now we have two terms. This is term 1 forward reaction and this is term 2 backward reaction. So in our case, term 1 is dependent only on concentration of CHCl3. Okay, so for that exponent of CHCl3, we took 1. Okay, and as the coefficient is 1, so we need to calculate k is 1. So ln k is equal to 1 is equal to 0. So all ABCD values are 0. And similarly for term 2, there is 0. So there is no backward reaction, right? So there is no dependency of concentration on rate, right? So all terms we need to give 0 and value of that ABCD should be ln minus ln0. So ln0 is minus infinity. So we took very large negative number from here if you see. Okay, let's say that we are given some backward reaction. Let's say it is 1 into C concentration of H2O square into concentration of O2. So what should we add if it is like that? 1 into concentration of H2O power 2 into concentration of O2. What should we add? Under term 2. Is question clear or not?
2, we need to add 2 become concentration.
See, I am saying that this instead of 0, what if we have 1 into C of H2O square into C of O2 raised to 1. So what should we add here? Concentration of H2O to the power 2. So exponent of water
Yes,
should be
sir.
2 and
2.
exponent of O2 should be
1.
1.
And everything else we should leave it like that. And as that value is 1, so this all ABCD should be 0, right?
0.
Yes, sir.
Okay. So in this case, there is no backward reaction. But if backward reaction is given to you, you need to add it like we added for term 1. Okay. I guess this driving force part is clear to everyone. Right?
Yes.
Okay. So
We
now
can
let's
add
move.
0 in term 2, no? Like instead of leaving it to empty, you can add 0.
Yeah, we can, if we are leaving it empty, that means that it is not dependent. So it will automatically take at 0. We can leave it empty. If you want to write it, you can write it. It's not an issue. Okay, so now let's move ahead for denominator part. This numerator we have completed. So the denominator is given as 1 plus something into C of HCl plus something into C of CHCl3. So our denominator should be 1 plus KWW plus KXX something something raised to n. Okay, so let's try to replicate this here. Okay, so what should be the adsorption expression exponent? What should be the value from
1.
here?
1.
Why 1?
N is equal.
N is 1. Okay, so this adsorption expression exponent should be 1. Okay. Now we need to add concentration exponent. Let's first add, okay, we don't need to add every term actually. So from here you can see that for term 1, there are 1, 2, 3 terms, right? So term 1 is independent of all concentrations, right? So there is no concentration dependency. For term 2, this term 2, it is dependent on concentration of HCl. And term 3 is dependent on concentration of CHCl3, right? So we have dependency for HCl and CHCH3. So let's keep those two terms only. Or okay, let's add everything. First, let's add everything. Sorry. Okay. So for term one, it is all zero. Sorry. I don't know why it's 0, 0. Okay, why I added 0? Because term 1 is just 1 plus something.
1.
So this term 1 is 1. There is no concentration term
ln1
in
is
term
0.
1. Okay.
Yeah.
Here, what should be the value of? No, it's not about ln1 is 0. We are adding concentration dependency. So there is no concentration term, right? There is no concentration of HCl, concentration of CHCl.
Okay.
So we can assume that CHCl to the power is 0. CHCl3 to the power is 0. So all those terms raised to 0. So that's why it's 0. For term 2, we have concentration of CHCl, HCl to the power 1. So we will add for HCl1 and we will leave all other terms. Okay. And
Why are
for
we
term,
leaving other terms? That's the issue. Like, why we need to leave?
sorry,
Why are
Sir,
we
who is
leaving?
asking?
Is
Who
it
is
like
asking? Yes,
Rohit?
Rohit. Yes.
Is there any reason why we are leaving it?
We
Why are
can
we?
write 0, 0. It's not an issue. It will automatically take, there is no concentration dependency for other terms.
Okay.
Dhruv, you are asking something?
sir, at the same question.
Okay. Okay, let's add 0. It's not a big deal.
Because when I was solving, I had only put the 1 and it was showing error for me. I don't know why it was saying that all parameters are not defined or something like that.
Okay, so let's add 0. I don't think it creates any issue. Okay, for term 3, what should be value for term 3? You guys will tell me. What should we add under term 3?
Sir,
Except
for
CHCl3, everything should be
HCl3
0.
we'll put 1.
Okay, for CHCl3, we will put 1. And for other terms, we'll put 0. Okay, so let's say that, I'm sorry, it's closed. Let's say that we are having more number of terms, right? The way we are here only having 1 plus kW into kx. So like here there were kw, kx, ky, kz. So if we are having multiple terms, we need to add for all those values, right? So we are only having 3 terms, so we added for 3 terms, right? Now for adsorption part, this part is completed. Concentration dependency part is completed. Now we need to add these constants, right? So let's first go to theory again, so it will be clear. So this exponent we need to give like this. ln k is a plus b by t plus c ln t plus dt, right? So under term 1, if we compare this with our problem, under term 1 is only having 1, right? There is no anything other than 1. So if we put k is equal to 1 here, that is k only, right? So ln1 is equal to this term. ln1 is 0. 0 is equal to this term. So what should be the value of ABCD?
0, 0.
All should be
All
0.
zeros.
So for term number, we need to write here term number 1. All coefficients are 0. Oh, okay, it automatically took 0. Wait, how to expand this? Okay. Okay, now let's go to term 2. I will just show you how to do it for term 2 and you will tell me answers for term 3. So here also term 2, 5.97 into 10 raised to 3, exponent of 2440 by RT should be in place of K, right? Right or not? We are moving very slowly.
Sir, so,
Please see.
yes, sir. Okay, sir.
Yes. So
Yes, sir.
see here, uh, this is the term. Is that term visible or not? I'm not sure. Okay, so you can see that 1 plus this is the denominator term I have written here. So 1 for term 1, ln k is this. This term 1 value is 1. So ln 1 is equal to this term. So ABCD should be 0, correct? For term 2 is value of k is whole this thing. 5.97 into 10 is to 3 exponent of 2440 by RT. So instead of in place of k in this expression, we will put ln of whole this thing 5.97 into 10 is to 3 exponent of 2440 by RT. That is equal to a plus b by t plus c ln t plus dt. Okay, this first line is clear or not? Tell me.
Yes, sir.
That's clear.
Okay, so we'll move ahead. Now we need to find the coefficients ABCD. It's not like 0. So we need to convert this left hand side term into this right hand side term, right? So this ln of 5.97 into 10 is to 3 is this 8.6945, and ln into exponent it will added as it will cancel out. For just saying it will cancel out. So this ln of exponent, this term will be plus 2440 by RT, correct? So we have expression like A is 8.6945, correct? B by T is 2440 by RT. So B will be 2440 by R. That is, R is given 8.314. So it should be 293.48. There is no LNT term on the left hand side and there is no DT term on the left hand side. So C and D will be 0. Is this clear? Or
Yes.
is this complex for you? Understand?
It's clear.
Okay, so let's add value of A as 8.6945 for term 2, 8.6945, and value of B was 2440 by R, that is 293.48, 293.48, 293.48. Okay, so we have added and C and D are 0. So we have added for term 2. Now let's go for term 3. So term 3 was given as this 1.23 into 10 is to 3 exponent of 5330 by RT. So you guys will tell me what should I add A and B. You guys calculate and tell me. Is this clear or not? I'll keep this screen open. We have this term. Just calculate value of A and B. There is no C and D term. It's similar to this only, right? There won't be any C and D term. Are you guys solving or not?
Sir, the value of A is 7.1147 something.
Okay, and value of B will be 641 point something.
Sir, yes, sir, 641.0. Sir, but the thing is,
Yes.
it is 5330 by RT. So should we also substitute the value of T when we are solving the...
See. Listen, what are you doing? You are comparing on both the sides, right?
Yes, sir.
So
Yes, sir.
2440 by RT. Okay, here 5330 by RT is equal to B by T, right?
Yes,
So
sir.
T is cancelled out, right?
Okay, sir.
On
Okay,
both
sir.
the sides. Just
Okay.
B is 5330 by R.
Okay, sir.
Okay, let's add 7.11477. 7.11477 for A and B is 641.0873. 641.0873. Okay. Okay. So I guess we completed this whole part of reaction. We added this whole reaction. Okay, the main pain of this problem. Okay, so let's simulate it. We need to add reaction here. Here we need to choose a reaction. So we'll just choose it and we will run the simulation. Okay, so our results are available. So it has converged without any errors and warnings. So okay, let's check what were the problem statements given to us in assignment. The first problem of the first question was the mole fraction of HCl in product stream. So let's go to product stream and results. And what is the mole fraction of HCl? Mole fraction of HCl, that is 0.727502, right? And your answer range was 0.7 to 0.74. So our answer is correct, right? Our answer is correct or not?
Yes, yes, correct.
It is correct, right? Okay, so next question is the heat duty of PFR in megawatt. So let's check what is the heat duty we are getting. Heat duty of PFR in megawatt. It's minus 5.16068. And the answer is in between minus 5.3 to minus 5. So we are in range, right? Minus 5.16. So this is also correct. The residence time of reactor is nanosecond. So here residence time in nanoseconds. So where is nanosecond? Here, nanosecond. That is 531968. 531968. So it falls between this range, right? Then the pressure inside the, okay, I will come to this question 4 after question 5. The question 5 is the net moles generated inside the reactor in an hour. So from where can I find net moles generated? Anyone? It's here only. We need to choose balance part.
In
So
balance.
net moles generated are 85.7567. So we are between 80 and 90. Correct? So the only question left is the pressure inside the reactor at the end of the third tube. What should be the value? What should be the value?
In profiles, it will get.
Sorry. In which
Profiles,
unit
profiles,
it is asked? Atmosphere, yeah. Okay, sorry. What were you saying? What
profiles,
were
we
you?
will be getting it.
From where profile? Here.
Reactor profiles.
Okay, where? Now. Here.
But no, no, setup and convergence report come down.
Here.
In profiles, you come down, come down.
Okay, in profile. Okay. So what is told at the end of the third tube? I guess it's third tube, right? At the end of the third tube. So tell the value from tube?
There are 10 tubes over there.
It's
Actually, it
very
is
logical.
for any tube it will be same.
Yeah, for any tube it will be same because your reactor is like this, and your fluid is flowing from that tube. So each tubes will have same value. So whatever the reactor is, whatever the pressure is at outlet or at the end, let's say the reactor length at last 1.2 meter, it will be the pressure at end tube, at the end of the tube. So that is 0.7895 atm. Sorry, what was the value? 7895. Okay, so we are also here also we are fine. Okay. Is this problem clear to everyone?
But in the
This
profiles, at the third distance, when the third tube completes, it will
Yes.
be something else. That's a reason which I have said go to the profiles, check there.
No, we can't because all tubes are like this. So all tubes will behave
But
identically, right?
across the tubes, the when the reactor length, the pressure is getting varied over there. Check
Yes.
that section.
Yes.
Yes,
He's
and
getting married.
at third tube completion part, then there will
See,
be some other difference.
see, what is your it is your length of the reactor is 1.2 meter, right? And your sorry, your length of the reactor is 1.2 meter, and there are 10 tubes, and diameter is 0.6 inches. So you need to assume that between this 0.6 inch length, there are 10 tubes placed, right? So all 10 tubes we can assume it won't be it should not be ideally 1.2 meter, but let's assume that all 10 tubes are 1.2 meter length in PFR only. So if from here to here, for all tubes, the values will be same, right? Why will it be different? I don't understand. Anyone else who wants
Uh,
to say something about this? Harshil?
No, no.
Can I ask different questions, sir?
Yes, please say.
Actually, I want to ask about the current assignment.
Okay, we'll go there. We will go there. First, let's talk about this problem only.
Okay, okay,
Sir,
okay.
most of the doubts are clear, but because the Aspen isn't opening, I cannot confirm whether and rectify my mistakes as of right now. So if anything else, I'll contact you via.
Okay, let's do one thing. Whoever is facing the issue, I have solved this problem. So just write me an email. I will share this problem solution file with you if you are facing any issues further. Is this fine?
Yes, sir.
Just write me an email, anyone who is facing. I will just share my, I don't know how to share this in
I think
common.
someone has already posted the link, not link, but the save file, Aspen file on the Q&A section.
Okay, then I guess it will be useful for every one of you, right?
Yes, yes.
Okay, so I want one of you to summarize this problem. Who will initiate? I just want to summarize that
Sir,
reaction part.
sir,
Okay,
I
Dhruv.
can.
Okay, I will keep this part open for you, so you can go ahead.
Sir, could you go into slideshow mode, sir? Yes, sir. So
Okay.
first we write the coefficients and exponents of the equation in the reaction because we need to define the reaction in Aspen after we have
Yes.
set the parameters and everything. Because it is
Yes.
a reaction rate consist in S minus one, which is a first order
Second
reaction.
index. First
Second,
order. Yes.
yes, sir. And the exponent of CHCl3, which is chloroform, is 2 and water is also 2. O2 is 1, CO2 is 2 and HCl is 6, and there is no
That is
backward.
no. That is not exponent. That is stoichiometric coefficient.
So yes, sorry, sir, stoichiometric
Yes.
coefficient. So
Yes.
and there is no backward reaction happening. So it is only forward. There will only be one reaction.
Yes.
After that, in the like adsorption coefficient driving force part, we will put the details of the equation of the numerator and the denominator. In the driving force part and the uh, adsorption coefficient that part, we'll put 3.72 into 10 raised to 5 as the k value.
No,
217.
I don't want answers. I just want to generalize it. Like what should be for for driving force term from
Yes,
here.
sir.
Just say it. I don't want answers.
Sir, so for from the bracket that is 1 into CHCl3 minus 0. So now here
Yes.
it is only two terms, so we'll only define for two terms. If there are more terms,
Yes.
we'll define for the rest of the terms. And if there is a value on top of CHCl3, that is the power, then we'll have to mention that as well as
Yes.
the
So that
exponent
is
of that.
exponent. Yes, that is
Yes, sir.
exponent. So CSCL3
And
exponent is 1 in our
one.
case. Okay.
And the rest are 0 because they are not mentioned.
Okay.
And in the denominator, this is the adsorption coefficient part. First term has no other multiple in it, so it will all be 0 and the only value will be 1. In the second term, the value of CHCl will be 1 and the rest 0, and we'll compare the results from the standard equation that is there with the values given here and find the values of A, B, C, and D.
And D for each values of K
Yes.
given to us.
Also,
This
for
just
the driving force part, also we'll have to derive one A, B, and C, and
yeah,
uh,
here it was 1 into CHCl3. So we just add ln1 is equal to 0. So
yes,
all ABCD are 0 and ln0 is minus infinity. So this any of this term won't be minus infinity as it is temperature dependent. So we assume that only A is very large negative number. Okay.
and then we'll continue doing it for the same in the adsorption coefficient, and then fill in the details and calculate.
Yes. Yes. Okay. This was a bit difficult problem and I don't know why they gave you in assignment. It is just this part you need to understand how to add these ABCD values, nothing else. And if it's, let's say if here it is whole to the power raised to 2. So our exponent, adsorption exponent should be 2, right? This n value should be 2. If it's here is 2, right? Right or not? This term 1 plus 5.97 into this whole term raised to 2 is given. Let's say if it's given like raised to 2, so our this value should be I'm sorry, or this value should be 2. Okay, there is no input here. Not in RPF, I'm sorry, in reactions. Here under adsorption we added adsorption expression exponent as 1. Okay, if it's raised to 2, here this whole term is in power of 2. Denominator is in power of 2. We will add here 2. Okay.
Yes.
So I guess this problem is clear to everyone. So we can stop this problem. And if you are having any query, you can check that file. Someone told that it's available somewhere, or you can write back to me. I will share that with you. Okay, so I just want to know who is having Aspen access right now. I just want to solve one more problem of hydrocarbon separation unit. So who can solve this? I have already solved, so it won't be useful for me.
I'm still not able to open the Aspen.
Okay, Sudhanshu, are you able to? You are also not able to, I guess. Okay, Manish, can you do it if it's possible for you?
No, sir. Aspen is not opening.
Okay, so I will solve that. Just I hope you guys do it by your own later. It's a good problem. It is the huge problem statement we have. So the problem statement is we are going for case study 6. The problem statement is a hydrocarbon stream H is at 5 degrees Celsius and 2.5 atmospheric pressure. The pump has discharged the liquid feed F at 5 atmospheric pressure. This is the flow sheet. Let's see the flow sheet first. From pump H, from stream H is what was the sentence here? Okay, the hydrocarbon stream H is at 5 degrees Celsius and 2.5 atmospheric pressure. So these feed conditions are given to us from H for H. The pump has discharged the liquid feed F at 5 atmospheric pressure. Okay, so pump what will do? What is the duty of pump? It will only increase the pressure. So the feed pressure is increased. The component wide flow rates are shown in table. So these are the values of flow rate given to us. So we have 1, 2, 3, 4, 5, 6, 7. 7 components: ethane, propane, isobutane, n-butane, isopentane, n-pentane, and n-hexane. So component flow rate of each components are given. In figure 4.62, the schematic representation of a hydrocarbon separation process integrated with a pump, 3 DHTW columns, C1, C2, and C3. So our C1, this C1, C2, and C3, these three are DHTW models and 2 rate frac columns CR1 and CR2. So CR1 and CR2, those are rate frag columns is soon. So what should we expect? There are 1, 2, 3, 4, 5. What should we expect? What should happen?
We expect C1 at the top of the top column and remaining rest in C3, B3 column, we should expect the VS.
Okay. So no, I am just asking from C1 column, what should we get? Which component should be in majority?
C2 to C4.
C2 to
And
C4. Okay, let's say
C4.
C2 to C4 is here from top. So what we are doing we are separating top and bottom from here. So from top, something is going into this CR1 column and its bottom is going, its top is going, and similarly here also. Okay. All DHTW fractionators have total 20 stages each, including condenser and reboiler, and two racked models have 10 stages each, including condenser and reboiler. With no reboiler, okay. So racked model is not having reboiler. Here there is no reboiler. These two columns are not having any reboiler. The specifications shown in table 4.12 A and B are required for simulating the process. So these are specifications from C1. C1 is this. Light key is 99% of NC4 and heavy key is 1% of IC5. For C2 also, it's for C2 it is isobutane, and for C3 it is isopentane. Okay, and other this condenser type and other things are given to us. For CR1 and CR2, we additionally need to give two conditions. So one is given distillate to feed ratio. We only need one condition because there is no reboiler. If we were having reboiler, we need additional input as let's say reflux ratio or something. So we are given these two tables. Applying the Pang-Robinson property method, simulate the separation process to compute the flow rates and composition of all products. Okay, so let's first solve this problem. Okay, I'm not going to save this as I have already solved. Okay. Oh, I was not supposed to close it. Try to solve it if you are getting some time. Then how are you going to complete your assignment 11? 11 or 12, I don't know. 11, yes.
That's it. In column section, there is multi-column section. Okay. Shall we use it? Can we use it?
Where?
Open the column section.
Okay. In simulations. Okay, yes, here.
Multi-fractionator or petrofrac.
You can do that, but in this problem, it is defined like this. You can do that. You can try with that. Not an issue.
Okay, let's first check what do you say, boiling point
Because
or
that
boil
part will be
point.
having some different specifications. It won't be exactly same, I guess. Let's try this the way it is given to us. Then let's see what we can do. Okay, so first let's add the components. Go to properties. Okay, so we have from butane to please. Okay, please at least one of you take the screenshot of the problem statement so I don't have to move from here to there. But I'm having the book. Just a minute. I'll just open the problem statement from book. Just give me a minute. Okay, so I am having the problem statement from here. But just take the screenshot so you can follow what is happening. This is the page 1. is 4.5. Okay. Then page 2. This is page 3. Okay, should I move ahead? Should I move ahead? Please respond.
Yes.
Okay. So so we have C2, ethane, and C3, propane. If from butane onwards, I will find from here. Butane, sorry, I'm writing anything. Butane. Okay, let's add the way it is given to us in problem. Isobutane. Let's first add isobutane. Then just butane. Add. Then we have isopentane. Okay, isopentane. Then we are just having pentane. Then hexane. Okay, so we have added all the components. I will just rename them according to problem statement. This is C2 and this is C3 and this is IC4 and C4 and IC5 and C5 and C6. Okay, so we have added all the components. Okay, there are 1, 2, 3, 4, 5, 6, 7. Okay, so I will now press next. Okay, so which property method is told to us? Check and tell me.
Peng Robinson, I guess.
Okay, it is Peng Robinson. So from method name, I will choose Peng Robinson. Okay, I will press next. Okay, so I guess everything is there. There is no option of compute using something other. Okay, so all this part is completed. Now we will go to simulation.
Let's check the K values first, so that we get an idea. Isobutane and butane,
Sorry,
isopentane and pentane. We need to know which one evaporates, which is volatile and which is not volatile, which is the heavy.
that we can
So
know from boiling point only, right?
yeah, boiling point or K values, anything can work.
Okay, so let's
First check
just let's just check the boiling point from here only. There is no need to
boiling.
go.
No, from the Aspen. From Aspen we can check it.
Yeah, we can check
Uh,
it, but okay, let's do it from here.
improper.
Analysis binary. No, it's
Yeah,
not binary. It's not binary.
it's not pure. Or else in the specifications, you can check the review. Like go to the setup, uh,
Just a minute, just a minute, just a
components.
minute, just a minute, just a minute. I need to delete this, else it will show some error.
Yeah,
Here,
yeah, component
specification.
specifications and bottom review is available at the bottom side. Pre-order and
Okay.
yeah, yeah.
Okay, it's taking some time. Okay, so what are we having? Okay, this is nice. Thank you for sharing. So we need
TB.
TB is here. Okay. So TB is lowest for C2, more volatile C2, C3. Okay, we have added in that order only, right?
Any order? Yes, okay.
We have added in that increasing order of boiling point only. P value is not given, right? No.
Yes, we'll go ahead.
Separation factor is not given. Okay, let's go to simulation window. So according to the flow sheet, I will add everything according to flow sheet. I'll go to column. Guys, just give me a minute. I need to close the fan. Just give me a minute. I need to switch the fan and close that door. Just give me a minute. Okay, so let's add the reaction. So we'll go to first pressure changes. From there, we'll add pump. Okay, I assume that all of you are having flow sheet, so just guide me how to do it. This is the flow sheet. Just take the screenshot if you are not having. Okay, just guide me. After pump, what is there? We have
Could you
column.
show it once again?
Okay.
Yes, sir. Sir, we have a column.
Yes. Okay. Can I minimize this?
Yes, sir.
Okay. So we have under columns C1, C2, and C3 are DHTW model. So let's first add this is C1 and this is C2
Sir, and
and
C3.
C3. And we have
CR1 and CR2.
two red flag.
Yes,
So
sir.
we need to first go to red flag. In red flag, it is RECT column.
Yes, sir.
So
Sir, the
this
yes,
one,
sir. Yes, sir.
yes, RECT. So RECT 1,
Oh,
CT 2. Okay, let's rename this part. Sorry, let's rename this. This is
pump.
pump MP. This one is
Sir, CR,
sorry,
C1.
just a minute. C1. And I guess this is C2, C2,
C3.
and this is
C3.
C3. And this one is CR1.
Yes, sir.
CR1. Um, CR2. Now let's add all the streams. This is our feed stream. Pump is going into column number
Sir, C1.
0.
Yes, sir.
Now from C1, it is going to CR1. There is one issue in diagram. It's from here, not from top. Okay, it's from this line, not from this line. Because if you go to okay, just give me a minute. We can't choose this. We need to choose this. It's not from here, it's from okay, let's wait for this stream. Okay, let's add first because here it's from top. So for that, okay, I guess it will automatically take if we choose that option. Okay, let's do it like this for now. Okay, and this bottom is going to C3 column, right? Okay, now this is not going anywhere, right? And this is going to C2 stream. No, this is also not going anywhere. Now, bottoms of this is going to C2 and vapor distillate is going to CR2. From CR2, liquid distillate is coming out, so it is a total condenser. And from bottom, it's like this. Okay, is this flow sheet correct? Can anyone check? Except for this part. Except for this part, is this correct?
Yes, sir.
No, we need to add these two inputs.
Sir, C2 we'll have to get
Yes,
output.
yes, we need to add that.
And sir, from C1, it is the output is from the top, sir.
No, we are not able to give
Okay.
it because we need to change this condenser type from. Let's wait for that part.
Okay, sir. Okay, sir.
Okay, this is feed. No, this is H. Then we choose align blocks. This is F. And this one is B1. D1. And this is D3. And this is B3. Same D2, B2. D2, B2. Then this one is BR1. BR1. Are you understanding nomenclature or not?
Yes, sir.
BR1. This one is DR2. Means BR2. Okay, so I guess flow sheet is completed. Yes, it is completed. Okay, so now let's go to input. Okay, so what is the condition given? What is the condition of H stream? Are you having screenshot or not? Wait. Please take it and
Yes, sir.
these also this part also.
Done, sir.
Okay. So let's now go to input of. We'll start with first streams. So H stream. What is the temperature pressure condition of H
5
stream?
degrees Celsius and 2.5 atm.
5 atm. Okay. And these values, what is given to us?
Sir, C2 is 0.35 kilomole per hour.
Is it 0.35 or just 35?
Sir, 35, sorry, 35.
And the unit is kilomoles per hour. Okay. So it is 335. Okay. Then
Yes.
C3
50.
50.
130.
130
N-butane is 200. Isopentane is 180. N-pentane is 200. And N-heptane is 5.
Fine. Guys, just give me a minute. I'm sorry, someone is here. One of my friend was here. Okay, so we have added these values, right? 5 degrees Celsius, 2.5 atmosphere. Okay, so we are done with H-stream. Now let's go to pump. So what is given for pump part? What is given?
Sir, the discharge pressure is 5 atm.
5 atmospheric pressure.
Yeah, the pump has discharged the liquid feed F at 5 atm.
So we will add discharge pressure as 5 atm. Okay. Now we need to give C1 values. So what is given for C1? Okay.
Sir, 99% of NC4 and 1% of IC5. 19% of NC4 is light key.
Okay. Now let's first add number of stages. How many stages are there?
Sir, 10, 20, sir, I guess.
Okay. Is that DSTW or C1 is DSTW or red flag?
Sir,
C1 is
DSTW considers the
DSTW.
total 20 stages, yes, sir.
Okay. So it is 20. Okay. What is this value? Okay. You are seeing this as for C1 and C4.
99% of NC4.
And heavy keys.
IC5 1%.
IC5. Okay.
Yes, sir.
That is 0.01.
01.
Okay. And what is condenser type?
Partial condenser with
with
all vapor
vapor
distillate.
distillate.
And sir, the condenser is 4.
Condenser
Pressure is 4 atm.
4 atm. Okay, we need to change the unit. And reboiler
4 atm,
also
sir.
same. Okay, let me just check if we can change this or not. No, we can't change it. So I guess it will automatically take this stream as vapor distillate. Yes, we are not able to add it from top. Okay, so we have given input for
C1.
C1 is done. Right, now let's go to
C2.
which one is next? C2. Okay, so this one is C2. So what is given? How many number of stages?
Sir,
Same,
same.
20. And what is light key for C2?
IC4. Isobutane.
Off
99%. Yes, sir. 109.
and
And
heavy
sir,
keys.
sir,
Yes.
2% of NC4.
Okay.
1.5 pressure of condenser and reboiler, and the type is total condenser.
1.5.
ATM.
They both are in ATM.
Yes, sir.
Okay. And the condenser is of total
Total
condenser.
condenser. Yes, sir.
Okay, C2 is done. Now let's go to
C3.
C3. Okay. So here also 20
20
stages.
stages.
Okay. Condenser pressure is
3 ATM and reboiler pressure also 3 ATM. And the type is total condenser.
okay. What is the error we are getting when we first change the condenser pressure? Condenser pressure cannot
Reboiler,
be greater than reboiler
reboiler
pressure.
pressure, reboil pressure will be always greater side than the
Yes,
condenser.
because it's in bottom, right? Now, what is
99% of IC5. and light key, and 4% of NC5 is heavy key.
4%, right?
Yes, at 0.04.
And condenser is total condenser
Total
here.
condenser.
Okay. So we have completed input for DSTW column. Now let's go to CR1 and CR2 columns. Okay. Let's first add for CR1. So how many number of stages?
10, sir.
10 stages. Okay, so I'll add here 10. Then condenser is
Sir, partial vapor condenser in CR1.
partial vapor condenser is in CR1.
And no reboiler.
Why no reboiler?
Sir, because in the design it is mentioned
No reboiler.
two rect models have 10 stages each, including condenser and reboiler, and then with no reboiler is also mentioned.
No reboiler. So we don't have here also, from here also you can see there is no reboiler from
Yes.
Flowset. So reboiler is none. So when we give none reboiler, one specification will be removed. Okay, it won't be removed right now, but when we will add this value, now what is distillate to feed ratio is given, right? Here.
Yes, sir. On mole basis, distillate to feed ratio, mole basis, it is 0.2 for CR1.
So see, there is only one option we need to give, as we are having only one reboiler. We are having no reboiler.
And sir,
Only
pressure
one.
is 2 atm.
Okay, let's first go to here. So what should be D1? There is nothing given about D1. What should we add?
Sir, 1.
Why 1?
Sir, it is top from the top.
It won't allow. It is not allowing 1. It is not allowing 1. This is CR1 column, right? Okay, let's keep it right now as it is. I will just press next. So let's see what is it saying. Feed to the bottom must be specified when reboiler is equal to none or reboiler duty is equal to 0 in the form of on stage feed to the number of stages or an above stage plus 1. Okay, so we should add on stage 10. On stage 10 or above stage 11. I'm just adding on stage 10. Okay. When there is no reboiler in the system, our feed should be to the bottom, right?
Okay. Yes, sir.
That's why it is not given in the problem. This is self-explanatory. Now, pressure. What is the value of pressure? What is the value of pressure?
Sir, 2 atm.
2 atmospheric pressure. Okay, so we don't need to give anything here for column CR1. Now let's go to CR2 column. Same 10 number of stages. Which type kind of condenser is it?
Sir, total.
Total condenser with
No reboiler.
no reboiler. And what is given here?
Distillate to feed ratio, mole basis is 0.5.
Distillate to feed ratio on mole basis is 0.5. Okay, so this part is clear. Total condenser. Okay. Now we'll go to next. Okay, so here what should be DR1?
Sir, on stage 10.
On stage 10 or above stage 11, right?
Yes, sir.
Okay. Then we'll go to pressure. What is the value of pressure?
Sir, 1.5 atm.
Just a minute. Okay, so this is also done. So required input complete. So we have given all inputs. Sorry.
Save
Okay,
the
we have
file.
given all
Save the
inputs.
file. Save the file.
Okay. Okay. I have already solved it. So if there is some issue, we can directly. Okay, it is saved. Let's press next. Okay, so our simulation is completed without any errors. So now let's see what are we getting from C1 column. We'll go individually, right? So from C1 column, we are getting, I'll go to mass fraction because that is easier for me to understand. Not mass fraction, sorry, mass flows. Huh. So here we can see that from C1 column, from here, what is expected? All C2 and C3, those are lighter components, should be in top, and all heavier components should be in bottom. So we are getting C1 100% C2 in distillate, 100% C3 in distillate, near to 100% IC4 in distillate, and other than this C2 and C4 is very less, but IC5, NC5 and NC6, these three are going into bottoms. There is no C5 and C6, 100% C5 and C6 is going in bottoms of here. So we need to separate C5 and C6.
IC5 is the design constraint, not like we kept it 1% there.
Yes. Yes. So, so we need one column to separate. From here, what were we having maximum percent of C5 and C6 from bottom. So what do we expect from here? Because this bottom we are giving it to a distillation column. So what do we expect?
C4s, C5s on top and C6 on bottom.
So we expect that 100% NC4, IC4 is on top, nearly 100% IC5 is also on top, and NC6, 100% of NC6 is in bottom stream. Correct. So we can say C6 and C5 are separated.
We'll check the design constraints also. In C2, C3, what is the design constraints like light key and heavy key compositions?
For C2, for C3, it is 4% of C5 in bottom.
Okay.
So that is what we
Okay.
are getting. So now what we can do, we can replace this DSTW with red flag column, and we can give actual inputs. From here, we will be able to get that minimum number of trays and all inputs. Okay. Okay. So here we need minimum number of 34 trays, and what we gave only 10 or 20. We gave only 20 trays. So here we need actual 69 stages, and feed stage should be 29, and we are given some additional values like reboiler duty, and we can give this reflux ratio. Reflux ratio is also very high, 8.57. So we can use these input and we can replace this DHTW with red flag model, right? On which method DHTW works, I assume you know.
Gill Underwood.
Sorry?
Gill Underwood. Shubman Gill and Underwood. Gill
Okay.
Underwood.
Then, okay, this part is done. Now this part. So from here, we were having, from top, we were having mixture of C2, C3. From top, we were having C2, C3, IC4, and NC4, maximum quantity of this four. Okay. So from top of CR1, from top of CR1 column, okay, maximum C2, C3, C2 and C3 only, right? C2 and C3 are going on top. There is no constraint for CR1 column. So we are getting maximum CR1, maximum C2, C3 from here. And to separate then C2, C3, we need one more column. So I guess that will separate C2 and C3. Okay. C2 is from top and C3 is from bottom. Are you following the chain or not? Guys,
Yes, sir.
please respond. Okay. From here, we got C2, C3, IC4. We send it here. And from here, C2, C3 mixer we obtained. And from here, we obtained C2 and C3 as pure products, right? From here, it was C5 and C6. So now we have IC4, NC4, and IC5, I guess. So let's check the results for here. I'm checking the correct column or not. It is C2, yeah. So that is based on constraint. So we are getting C5 from bottom expected and maximum NC4, no, C4, NC4 and IC5 from bottom and IC4 from top. These three from top. Okay. Okay. Is this clear to everyone? So for this column, what is the number of stages we require? I guess it will be more. Oh, those are less. Only 45 stages are required with feed stage location of 21 and reflux ratio and all these inputs. Okay. So what we can do now, we have minimum requirements with us. We have this minimum reflux ratio, actual reflux ratio, these things are with us. So what we can do, we can replace this column, DSTW column with rate frag model, and we can get actual results. What was the number here for C1? Okay, for C1 the number was only 11. No, 20. Okay. In feed stages in between 10. Okay. Okay. Okay, so I guess none of you is having Aspen right now, right? So if you can try this by your own. You can add this, replace this DSTW model with red frag model, and you can actually simulate this process. And you can. Do you want me to do it right now? If you want, we can do it. Okay, no one is saying no response I'm getting, so I guess you will do it. So it's still 7:45 only. Sorry. Okay, no one is saying, no one is not saying. Yes, Sudhanshu. No, I guess he's not. Sorry, you are not audible. I guess you are not talking to us. So this was all about this week's problem. So let's now go to last year's assignment. Very easy problems compared to your assignments. So okay, I have two files this time open, so we don't need to scroll from top to bottom. So we'll read question from here and we will see diagram from here. So this is some diagram. B1 is input, S1, S2, S3. Okay, this is some shortcut method based on some shortcut method. Okay, so these inputs are given. So let's see what is the problem. The block B1 is. Okay, what is block B1? Block B1 is of which type? Is it red frag? Is it
Red frag.
DSTW? Is that red frag? How can you say is that red frag?
Still on top it is written.
Yes,
Still.
here it's
Distill.
written still. Yes. So see here in this problem, in our problem, see you can see on bracket of C1 it is written DSTW. So it is kind of DSTW model. And here it should be red frag. So it is written CR1 red frag. Okay. Be careful with these questions. You are going to get, I guess, these questions only in your exams. This kind of questions in your exam. Okay. So answer is distill. The distillate to feed mole ratio in input A. Distillate to feed mole ratio. Okay, what should be the value here? Distillate to feed mole ratio. Anyone? The S2 is your distillate stream. S3 is your bottom stream and S1 is your feed stream, and some inputs are given, some output is given to you. So can you tell me what is distillate to feed rate? Distillate to feed ratio?
S2 by S1.
0.9.
Molar feed ratio. Okay. It is okay. Distillate is sorry S2 by S1. So what is S2 by S1? 10 by 100, right?
10 by.
Yeah, it is
Yes.
0.1.
Okay. Distillate to
Yes,
feed
sir.
ratio. Distillate is your S2 stream and feed is S1. And it is mole ratio. Okay. So you need to check molar flow rate. So molar flow rate is S1 is 100 and S2 is 10. So the ratio is 0.1. So answer is in 0.09 to 0.11. Okay. The condenser type input at B. Okay. Condenser type at input B. Okay. What is the condenser type? You don't need to see anything. This part, this enough. This is enough. What is the condenser type? No, what is
Total
condenser type?
condenser. Total condenser. In phases, it is liquid only.
Total condenser, liquid phase
Okay.
only.
Okay, so it is total condenser. Correct? Now, condenser pressure input at C. Condenser pressure input at C. C is here. Okay, what is the condenser pressure? Condenser is on top, right?
HS2. So it is 1 atmosphere.
1
Sir,
atmosphere.
1 ATM.
1 atm, and what is the unit here? Okay, no unit. So you assume that it is in atmospheric pressure. Okay.
No, sir, it will be given at that
Here.
where
Yeah, I agree.
the
Here.
letters
It is
are
180. Correct.
written.
Yes,
Yours
here it's
is
in ATM. Okay. Then reboiler pressure.
1.2.
Reboiler is S3 stream. Okay, so it should be 1.2 atmospheric pressure. So it should be 1.2. Okay. Now, okay, one more problem. Okay, let's open problem here. Okay, some design specification is given. Okay. There is no problem statement. Just give me a minute. Okay, design desk spec. Okay, it's mentioned here. Okay. So the question is type. What is the input at E in figure 4 is? What should it be?
Streams.
Why streams?
Same variable.
Sorry.
Same variable. It should be streams and then go to molar flow. In stream section, it should be molar.
Sorry, I'm not following you. What are you saying? Hello?
We need to
Type
select
mole flow.
streams here, and then we need to select the what type of stream, like molar flow, and then in that coming next part is substream like nitrogen, hydrogen.
No. Okay, yeah.
Answer,
The question
answer
is
of A is the mole flow, I think.
sorry.
Mole flow type,
Okay,
should be
why
mole
mole
flow.
flow?
because in mole there
Mole fraction.
showing.
Mole fraction. Mole
Here
fraction.
Yeah,
you
sorry, mole
see
In
fraction.
the
Mole fraction.
definition, it is written, sir. Yes, sir.
mole fraction stream S2. Okay, so it should
Yes.
be mole fraction. Okay, then next question is the input B. What should be input B of stream?
S2.
It's 2.
Why S2? Why
So
S2?
in the
Written.
definition, it is mentioned, and
Written in the
we are
document.
varying from it.
Definition.
Stream is S2. Okay. Then input C of which substream? Substream is
Mixed.
mixed.
Next.
Okay. And D, input at D is what is component? Clear.
Methanol.
Is
Ethanol.
clear. It is methanol. Okay, so this is all about your assignment, last year's assignment 11. Okay, these three questions, if you want to see, I have not followed this. If you want to see, we can, while performing calculations using sensitivity analysis tool, it was found that the increase in flash temperature leads to decrease in the molar flow rate, but improve the quality of diphenyl without recycling stream. This is based on your case study of week 11. These three questions, first three questions, you can have a look of first three questions. Did you follow what was your case study for week 11? Hello,
Yes.
what was your case study for week 11?
So one is this hydrodealkylation of toluene,
Okay,
and
hydrodealkylation of toluene. Then
then one is this LHHW one.
LHHW. Okay, and
Yeah, last one I don't remember. I have not solved it yet.
okay, so anyone who read, who followed these problems, who followed the.
The nitric oxide production plant.
Okay, so was that something about this diphenyl production? I guess it will be in LHHW, I
It
The
guess.
was first. It was
hydrodealkylation of toluene in it is in that one
it was
diphenyl.
yeah.
Okay,
It will
yeah.
be in the first one.
Okay, so just see these first three questions and tell me if answers are right or not. If you have correctly followed the lectures.
Flow rate. Yes, it's true. First is
First
true.
one is true. Okay,
Yes, yes. Today only I did that lecture.
okay.
The
Who's
last
this?
one is false, and the
Third
rest are
one,
true.
last the last one is from
Very
second case
fine.
study of that LHHW model. It is
Okay,
false.
last one. Reaction for formation of isobutene from isobutane is irreversible. No, it won't be irreversible, obviously. Okay. Okay, so this was all about.
There are some doubts regarding the assignment that I've mentioned you, sir.
Yes, can you share your, okay, your Aspen is not,
Sir, I've shared you already once in the morning, sir.
no, your Aspen right now is not, okay,
Right now it is not working, sir.
okay, I just have to see which was that week 10 part 2, I guess this one, right?
Yes, sir. This was also there, and sir, I got most of them wrong for some reason.
Okay, let's check. What is the reason? I told you to re-verify everything.
Sir,
I don't know.
I changed everything and re-verified as well, but still the answers haven't matched.
Okay, let's check. Let's check. Okay, it's not week, it's week 10, right? This week 11 problem is very easy, I guess, for every one of you, right? Or not? This is very easy
No,
Sir,
problem.
it's
no, sir.
just a plug flow reactor.
I just want a question
Just a
from.
question. In the conversion of PFI, it should be in percentage or it should be in 0 to 1?
I don't know. I have not designed the problem, but it's not written in you just mail them.
Yeah,
This is
because
confusing. This is
this is
confusing.
confusing. This is the confusing part.
This is confusing. Okay, you if you write in
No,
percentage
no,
and
no, I
yes,
think it should be between 0 to 1.
0 to 1.
Conversion
I am
can
I
be
am I am
done
writing
from 0.
it between 0 to 1 itself. I'm not considering as percentage since it is not
They have
given.
not mentioned actually percentage conversion, so I guess 0 to 1 is fine. Sorry, where
Yeah.
were we here? I guess this week's problem is very easy.
So, sir, I want to ask a question.
Yes.
in the assignment part B.
Assignment which one? 11.
This one, yes, yeah.
Okay, say.
Part A, there is a mention, sir, in second stanza, choose chemical with metric units.
Yeah,
When
from here.
when I
Here,
choose
here.
chemical with metric units, by default NRTL is showing.
Why?
So how could I
From
change?
here, no, from here, go to first properties
Okay,
and then wait, yeah. Then keep these as metric. No, it should not show by default NRTL. It has nothing to do with property method. It has just to do with this part. This
No,
part.
sir.
It has
While opening, no, you use it in Aspen. We get an option of
okay,
from
yeah,
this,
choosing that
here,
yeah,
metric.
here,
from this
here.
one, yes,
Here, chemicals with which unit?
English unit and a metric.
Yeah, here you need to choose here metric and chemicals with metric units. Okay, yeah.
Yeah.
It's saying that. Okay, you need to do it like that. This problem is only in reaction
So, sir,
part
but
because
if I choose the same as you
But
had,
now,
sir, so NRTL is by default here.
yeah, here property method is by default and let's wait. Let's just check. New simul. I guess it will take, right? Open selected
So
template. Just a minute.
from right corner right side you can open it.
Please just a minute. Just a minute. Just a minute. Just a
It's
minute.
okay.
Here. Okay, I'm just choosing it. Okay, I will just directly go to methods specifications. And I tell, but you can change, right? You what is given to you?
You can change and you can from the selected methods you can delete the NRTL.
And yeah, it is
Then
done, right?
And
so
from the
how to
selected
delete
methods
NRTL?
you can delete, sir.
How can delete?
Yeah, just
Okay,
delete it.
from here. Okay.
Okay. Metric
Okay.
with chemical. Okay.
even I
So
have done the same. But is this right way to do this?
sorry. No, go with this part only.
What?
Just go to, no, here they have written that chemicals with metric unit template. So do it like this only. Go to file and from here only chemicals with metric unit this template. Do it in this way only.
Okay, okay.
Because the issue is with the K. I guess it is the, yeah, it is issue with this K1 and K2 values. Here this K1 and K2 is given with this template. With this particular template only. So if you choose something else, then these values of K1 and K2 won't work. It's
No, sir.
the
I think I tried it. The same thing. The
yes,
same
please.
thing that you have means teach us like the LHHW,
Yes.
but the difference is uh, a message is appeared like an RTL method is not covering hydrocarbon, something like that. So that's
But
why I
we are not choosing an ideal method now for this.
so
I'm not
when,
understanding what you're saying.
actually when we choose the template, this one means chemical.
Yes.
Uh,
Yes.
Error is showing like an RTL method is not including hydrocarbon. This type of error is showing.
But did you change the property method from NRDL to something else?
I, yes, I changed it, but not remove the NRTL method.
No, remove it. You don't need
Okay,
NRDL.
okay.
Just remove it.
I'll check it after removing.
Okay, you don't need NRDL method, right?
Okay.
Okay, sorry, where were we? Okay, this problem is easy, right? I guess, right? Okay, I suggest you just ask this conversion part to uh, write an email. I don't know whom to whom, but write an email. Here you can see the conversion is 70%. So just write an email. So it's these two are very easy parts. So you should not miss these one points. Okay, so we were at Dhruv's part, week 10. Quiz 10. What was the okay. So heat duty. Which one did you get wrong?
Sir, all this from 6 to 9, 10, 9 I got all wrong,
Okay,
sir.
all of you wrong. All answers
Yes,
wrong.
sir.
Okay. So heat duty here was okay. I need to rerun. Okay, did anyone get full marks? 462.
Yeah, I got it. I got 100 out
Okay.
of 100.
Yes,
So there
yes.
are some. Okay, so we can check this. Just a minute is running. Is this flow sheet correct? If any one of you remember.
Can you minimize it?
Yes, just a minute. It's running, so it's
Uh,
not taking.
I have one input actually. I think we have to run
Uh,
everything after optimization. If we have run it before
Yeah, after
optimization, then all
optimization.
values will be incorrect.
oh, that is the issue.
After
Okay.
after design spec, you need to run it.
Okay. Carry out a design specification study. Okay, Dhruv. So how did you run it?
I run it after optimization also before optimization and checked all the values.
But nothing is
And
matching.
yes, sir.
Okay. I guess this is before or after. I don't remember. How was this?
You had
Uh,
deactivated it, I guess, the optimization in the design spec part.
Just a minute. Let me check. Oh, where is it? Here. Design specs. Activate it. Okay. Now let's run it and check. I guess then it will be some issue with input only. Yeah, this is not actually clear.
minimize the this one.
Yes, it's just a minute, just a minute. I actually forgot to do that and no, it won't happen. Just a minute. Okay, so before ending, I have something to share. Next Monday, we are not meeting. You will get an email. Next Monday, we are not meeting. Instead of next Monday, we are meeting day after tomorrow on the same time. I am
Okay.
traveling actually. I'm traveling from Friday, so I am not here. So we can do one thing. I have prepared one naphtha fractionator, some kind of problem. And what we can do if you are having any issues with your assignment 1 to 12, just write me an email if possible by today only, so we can solve that problem. And I will show you that big problem, but I guess we will not be able to complete that big problem within 2 hours. So I will just show you the part of the problem, how to do it, and rest you can try by your own. And we can simultaneously we'll start with first assignment queries. Are you having any queries in previous assignments or not? That is the first question.
The assignment 10 actually, the first question is which type of stream it is. Should be work stream, right?
Okay, assignment. I'm sorry, can
10,
I just
10.
I'm sorry, can I just end complete this question first?
Sure, sure.
So here heat duty of second separator is 1.056 and answer is point. So first one is matching, right? True.
For me, wait, I'll
I
check.
said the same file. If you see, net duty is 1 point, heat duty is 1.05668 kilowatt. And yeah, 1.05. So it is between 0.99 and 1.1, right? Then Vapor 2, yes.
I had gotten 1.161 and that is why it is, I guess, wrong, sir.
But how? I said you this file only, right?
Sir, and I did the exact same and I activated the design specification and ran also and same file I had ran, sir.
I guess you check it again. See, I'm doing that only. I activated it.
I'm trying to open the Aspen, but it is not opening right now.
Okay,
It's fine,
so
sir.
you check it
I'll
again and then tell me. Okay.
okay, sir.
Someone was asking about which part? Sorry. Question one. Who was asking?
Yeah, yeah. Yeah, I'm asking.
Asutosh.
Yeah.
Which one? This question only, right?
Yeah.
The
Question one.
dotted line from figure 19 represents. Dotted line from figure 19. Yeah, this is correct. It should be heat stream, energy stream, right? What is
Uh,
the doubt here?
no, no, it is see, when we check in Aspen, there is like three options: material stream, I think heat stream and work stream. There is no
No,
option
but
as energy stream.
no, but from here, okay, you are saying
And work stream shows same structure, like that same dotted one.
no.
No, no, no,
I'm
no,
not.
no, no. There is a big
I'm
there is
not.
a big difference. in three system, like work has a dot, and something has dot with the plus with mark, and third one is just dash dash dash.
Okay, I
Yeah,
am not.
so I checked all, but it is matching with work stream only. And there is nothing called energy stream in Aspen.
Okay,
There are only
see,
three
okay, I
types.
am saying, okay, let me say something. I don't know about which these three streams are available or not. I just told you energy stream based on logic, because if you can see that heat released, there is some heat integration network here. So you can see that heat is releasing here. Okay, so that heat released
Yeah,
is given here. So based on that only, I told you
So
energy
you are
stream.
you are right, Prasil sir, but you can correct it by using Aspen Plus. Just open it, and
Okay. Okay, I am not knowing this. Okay, just give me a minute. I
yes,
will.
and on
Okay.
simulation environment,
Yeah. Tell me what to do. Okay,
there is
let me go
material.
to new.
There is
Let me go to
in
new. Let me just a minute. Let me go to new.
so
Dhruv,
I
get back to
actually,
me if you are not getting big this
oh,
thing.
very simple thing, sir.
Sir. Yes, sir.
Okay. Yeah. Okay. In simulation. Okay. See.
In simulation mode, this go to model palette, and
Yeah.
this is material stream here. Arrow is one side.
Okay. You are
Yeah,
saying this
this
material
one
heat.
material heat and work power. There is a big difference, sir. One thing is yeah,
Okay. These dots. Then
yeah,
these dots. Okay. These are very small dots.
yes.
Power
This is
dots
watch
are.
and then
Okay. This is completely looking different, right?
this is the difference.
yeah, and if you look at this, it is matching with work stream only.
No, it is different.
Maybe,
Oh,
Workstream, no,
but
Workstream has dash. Here,
yes,
wait, let me zoom
yeah,
it out. Okay, wait a minute. Okay, let
zoom it.
me. एक minute, just a minute, just a minute. Here, see, you can see that these are dots. No, these are lines, not dots. Wait.
yeah, but uh, from available options, it is matching closely with work only. Because if we look at that heat,
Yeah,
heat stream,
I understood your concern. Okay.
so by logic, even I agree that it should be energy stream only.
Yes.
But I changed
Okay,
actually.
okay, does anyone know from
Sir,
here how can we
zoom.
add energy stream?
Sir, maybe try it between heaters because that
Okay,
would give different
let's
sort of
try it with heaters. Okay, let's one heater here. Okay, sorry, I need to one and one. I just delete this. Okay, and this is also not matching. Okay, so from heater, I don't know how to edit. Okay, let's. Sorry. Mm, but I guess we will require some actual values.
Sir, this is a material. This is a material stream.
Yes.
You should add heat stream. Sorry, energy stream or heat stream. Yeah. Then yes.
Let's say I'm just giving some random values. Okay, but it is showing long arrows, right? Okay, it is something different.
is it a
Can,
difference between
can you
Aspen
try
12
with
and Aspen 14?
No, no, it won't be like that. This is Aspen 14. Okay, there is no material stream, no momentum. Okay. Okay, ideally it should be energy stream, but I don't know how did they find this option.
Yeah, I agree. So even I selected first energy stream only, but just to confirm, I went here and checked those options. So there are from the available options, I think only work stream was making sense because
Yeah, yeah.
yeah,
If you match those dots, this thing, then box stream matches well. But
I-
logically, it should be energy stream. Okay, let me get back to you with this part. I don't know how did they even prepare this flow script. I will try something and we can do this on which day after tomorrow, Wednesday. Okay, guys, are you having any doubts in other previous assignments from 1 to 11? Other than we solved that LHHW part, other than that LHHW, yeah, please say. Hello? Was there no? Oh, I'm not getting any response. Please say something. Okay, so just it's a small request. If you are having any queries regarding assignment from 1 to 12, I don't know if 12 is available or not. So if you are having any query, please write me back. We will be meeting day after tomorrow, and I expect that you will join because that is the last lecture from my side. It is the last session from my side, not lecture. Okay, it is the same timing, 6 to 8. Okay.
On
Yes, sir.
Wednesday.
Wednesday, day after tomorrow. I guess we will get an email maybe tomorrow or tonight. I don't know.
Okay.
Is this
Sir,
time
in
fine or not?
Yes,
sir,
sir, it's fine.